elasticity of structures. The concept of incorporating seismic design procedures in building design was first adopted in a general sense in 1920s. It's almost 100 years ago in USA, where the importance of inertial loadings of buildings began to be appreciated. Nowadays, there is increased awareness that excessive strength is not required or even not necessarily desirable. It has been accepted that seismic design should encourage structural forms that are more likely to possess ductility and capable of undergoing large deformations. I hope during the course of this FDP, participants will be exposed to a wide range of topics, where lectures are rendered by experts on different themes, from seismology aspects to recent advances in earthquake resistant design, from numerical methods to experimental techniques. As Principal Sir just mentioned, it is very much essential that participants have to actively attend these courses to get the maximum output. I am absolutely certain that the knowledge we gain through this FDP will be advantageous in enhancing our knowledge and broadening our horizon in the field of earthquake engineering. This can contribute more effectively in delivery of courses to our students and in actual practice to perform the seismic design in a more effective manner. I wish you all an inspiring, fruitful time and a learning curve during the next 5 days. And my special thanks to the organizers for inviting me to be a part of this FDP on earthquake engineering. Thank you one and all. Namaste.
Thank you, sir. Next, I would like to welcome Dr. Anjali MS, HOD, Department of Civil Engineering, LBS CEK, for briefing the overview of the FDP.
Good morning, respected Principal Dr. Mohammed Shukur sir, our Chief Guest of the day, Professor Katta Venkatramana sir, Principal of LBS Institute of Technology for Women, Jaymohan sir, Deans, Heads of various departments, the course coordinators, my dear participants and my colleagues. I'm really proud and glad to be here in the inaugural session of this IICT Training and Learning Academy, adult-sponsored online faculty development program on advances in earthquake engineering. First of all, let us have a glance at the Department of Civil Engineering. It was established in the year 2008 and was affiliated to Kannur University. And presently it is coming under the APJ Abdul Kalam Technological University. The department is having good academic excellence and is undergoing consultancy projects for various government departments and organizations. In addition, the civil department is carrying out projects in collaboration with government departments. The students are also encouraged to participate in consultancy projects, which will be beneficial to boost their knowledge. And we, the faculty and students, are also involved in socially responsible projects. And the department, as well as the institution, are far ahead in such activities. Now, I would like to give a brief overview of this 5 days online FDP program. As we all know, AICT Training and Learning Academy ATL has been conducting FDPs for imparting faculty knowledge in trust and emerging areas. So with this point of view, we have selected the area as advances in earthquake engineering. And this FDP is intended to enhance the knowledge by learning the subject besides promoting skill in applying the technology. So the main objectives of this FDP are to make the participants familiar with the concepts of earthquake engineering, to provide foundational concepts of seismic testing of structures, and also to update the participants about the recent trends in seismic analysis and design. And these resource persons are the technical experts in this field. And the first session will be handled by our chief guest professor, Dr. Katta Venkatramana sir from the National Institute of Technology, Karnataka, Suratkal, who is a renowned professor in this field. And we also have Dr. G.R. Reddy from NITK Suratkal and Dr. Tamisar Rasim, SVNIT Surat. And Dr. Ajay Chaurasia from CSIR Central Building Research Institute, Roorkee, and he will be discussing on seismic resistance buildings. And we also have experts from CSIR Structural Engineering Research Center, Chennai, Dr. Satish Kumar K and Mrs. Srikala Madam. And both are working as chief scientists in advanced seismic testing and research laboratory. I'm sure that we will be able to get a practical exposure on contemporary seismic testing from them. And the session on ductile detailing of reinforced concrete structures will be handled by Dr. Leon Raj, scientist from CSIR Northeast Institute of Science and Technology, Surat, Jorhat. And the recent advances in earthquake-resistant construction practices will be shared by Dr. Sreyasvi C., seismic hazard modeler, working at Global Earthquake Model, Pavia, Italy. And this earthquake engineering is incomplete without the ground response study, ground motion prediction equations, and some and related geotechnical investigations. And these topics will be discussed by Dr. Jaya Madam from CET Trivandrum and Dr. Jay Mohan J from our sister institute, LBS Institute of Technology for Women, and Dr. M. Beenamol from our institute. Another important topic, like seismic design of liquid storage tanks, will be handled by Dr. Gigi Anna Varghese from GEC Barton Hill, Trivandrum, and we'll be having a very interesting session on habits and its influence on goal achievement by Mr. Hari Krishnan Nair and J. We have the participants, including the faculty members of AICT approved institutions, research scholars, then PG scholars, then other participants from government and industry. And this total FTP consists of 14 sessions with 3 sessions per day. And it is conducted purely in the online mode. And we expect that the participants, after the successful completion of the course, would be able to learn the basic concepts of engineering seismology, so the seismic resistance of masonry and confined masonry buildings, tactile detailing of RCC structures, etc. So I think more than 150 participants are registered for this faculty development program. On the last day of the course, there will be an objective assessment test, and digital certificate by Adult Academy will be awarded to the successful participants. The requirement of the FDP, more than 80% attendance and score more than 60% in the test. And I request all the participants have a good internet connectivity. And obviously, this course would be highly beneficial to the participants, and expecting your wholehearted support for this venture. The participants can also share their knowledge in this field so that it will enrich the energy of the resource person and make an active open discussion among us throughout the program. And I wish success for this online FDP. Have a nice day. Thank you.
Thank you, ma'am. We are moving on to the felicitation. I am welcoming Dr. Jayamohan J, Principal, LBS Institute of Technology for Women, for felicitation.
Thank you, Professor Sruthi. So, good morning, all of you. Our respected Chief Guest, Professor Katta Venkatramana, our respected Principal, Professor Mohammad Shukur, then my colleagues of Civil Engineering Department of LBS College of Engineering, Kasaragod, Dr. Anjali, Professor Radhika Nair, and Professor Beena Mode, Professor Sruthi, and my dear friends and colleagues of LBS College of Engineering, Kasaragod, Dr. Praveen Kumar, Dr. Vinod George, Professor Jayakumar, Dr. Shiva, Dr. Smita Mode, Professor Vinod Oyam, and Professor Vinish Kumar. At the outset, I want to appreciate the Department of Civil Engineering of LBS College of Engineering, Kasaragod, for organizing such a magnificent program. And I was very happy to see the resource persons, and they have brought in a lot of experts from NITK, SFINITY, Surat, and SCRC, CSIR, and government colleges, etc. And also there are many consultants, etc. And as our chief guest pointed out, now the design of structure subject to earthquake loading. So that is utmost prominence now. I think, and as you might observe, see nowadays these earthquakes are occurring in many new places. That is on the places where it never occurred in the past. So it is imperative that all of us have a good idea about how to design structure subject to earthquake loading, and these earthquakes cause as our chief guest pointed out, they cause this lot of loss to property and life. And I wish this FTP a grand success, and also agree with the principal, Professor Mohammad Shukur, that all the participants should attend the course sincerely, and they must apply this knowledge in their field. And my best wishes for the program. Thank you.
Thank you, sir. I am welcoming Dr. Praveen Kumar K, Dean Academics, LBS CK, for felicitation.
Respected Principal, Dr. Mohammad Shukur, sir. Today's Chief Guest, Professor Katta Venkatraman, sir, from NITK Suratkal. Other dignitaries joined with us today. And participants, my colleagues, dear friends, a very good morning. In fact, I'm really happy to join with this FDP inaugural session for the first time, that is conducted by the Civil Engineering Department of our college. At the outset, I congratulate all the faculty members of the Civil Engineering Department for initiating and getting such an adult FDP from the KICT. In our college, the Civil Engineering Department was started only in 2008, though our college was established in the year 93. But the history of civil engineering is for more than centuries. As far as India is, our country is concerned, we had a lot of earthquakes, especially in the northern areas and in the islands, which caused a lot of loss for our country in terms of man and money, as our chief guest told. What I understand from all this talk from the experts is that our construction technology is still in the development stage to face the sufferings from the such earthquakes. We had a very big earthquake in 2001 in Hoots. And after that only we actually started the many institutions and started many courses related to this, like National Information Center for Earthquake Engineering and many 4-year programs in national level institutes. So the topic is very relevant. I hope that all the participants will attend this FDP very sincerely and will benefit, so that it will be beneficial for your students as well as in your research activities. I wish all the success for this FDP, and once again I thank to the coordinators for giving me an opportunity to be a part of this. Thank you.
Thank you, sir. I would like to welcome Professor Jayagumar M., HOD, Electrical and Electronics Engineering Department, LBS CEK, for felicitation.
Respected Principal, respected Chief Guest, Professor Katta Venkatramana sir, HODs of departments, deans, all the participants, and my dear colleagues. I'm very much happy to be on this occasion to address to you all regarding the FTP on a very, very relevant topic. Nowadays, humanity is facing a lot of issues, and one of those major issues is earthquake. And I think India has given comparatively less importance to the management and the engineering side of the earthquake. So it is a very relevant topic, and I appreciate the HOD Civil Engineering Department for organizing such a wonderful program. And even though there is very less number of staff in Civil Engineering Department when compared to other departments of the college, the force they exert in pushing the department forward is extraordinarily high, and this is a matter which is to be appreciated. I wish all success to this venture, and I'm very much thankful to all the staff of the engineering department for inviting me to this session. Thank you.
Thank you, sir. Next, I would like to welcome Dr. Shiba K., HOD, Electronics and Communication Engineering Department, LBS CEK, for felicitation.
Thank you, Radhika Miss. Respected Principal, Dr. Mahmood Shukur sir, our honored guest, Professor Katta Venkataraman sir, respected Principal of IBS, LBS ITW, Kujapura, Dr. Jayamohan sir, all other dignitaries and all other guests gathered in this inaugural function. Actually, I am very happy to be a part of this program being organized by Civil Engineering Department. And I think this is the 4th faculty development program that is organized by various departments in our college. Actually, it is a very good achievement in this pandemic. In the start of this pandemic, everything is in a standstill. Now we are all acquainted with this situation. That is why we are able to save losing one academic year, and we could successfully conduct many such online programs and activities. I'm not extending too much. I would like to congratulate the coordinators, Dr. Binamal Miss and Professor Radhika Madam, for conducting such a program, and entire Civil Engineering Department for their effort to make this as a success. Actually, this topic is a very socially relevant. I understood that in this previous talks. It is a very good socially relevant topic and interdisciplinary branch of studies. And it is a good role in protecting our society. So I would like to congratulate once more the coordinators for choosing such a good topic. And I take this opportunity to express my gratitude for giving me this opportunity, and I wish all success to this program. Thank you. Thank you, everybody. Have a nice day. Thank you.
Thank you, ma'am. Next is a felicitation by Dr. Smidamol MB, HOD, Computer Science Engineering Department, LBCK.
Very good morning to all of you. I personally feel the topic is very relevant and attractive, and I wish to congratulate the Civil Engineering Department and the coordinators for choosing such a relevant topic. And I wish all the best for the program, and thank you.
Thank you, ma'am. For delivering vote of thanks, I would like to welcome Dr. Beena Molam, Course Coordinator, Assistant Professor, Department of Civil Engineering, LBCK.
Good morning, one and all present. First of all, I thank the Almighty and ask for His presence throughout the FDP recent advances in earthquake engineering. Now, I would like to thank our principal, Dr. Mohammed Shukur sir. He always extends his full supports on all academic and non-academic activities. For this FDP also, he encouraged us and gave us full support from planning to executing this FDP in all aspects. Thank you, sir. Now, I would like to thank our chief guest, Professor Dr. Katta Venkataramana of NITK Suratkal. He is here for sharing his valuable experience and for boosting our professional knowledge in earthquake engineering by his nice inaugural address and the first FDP session. Thank you, sir. Now, I would like to thank Dr. Jayamohan sir, Principal of LBT Trivandrum. He is always ready to support us whenever we reach him for any help. And we always feel Dr. Jayamohan sir as one among us. Thank you, sir. Thank you for all your support. Now, I would like to thank our HOD, Dr. Anjali Miss. Under her leadership, the Department of Civil Engineering is growing day by day in all dimensions. She has extended her full support and guidance for this FDP throughout our phase of planning to the execution. Thank you, ma'am. I thank the Deans, Dr. Praveen Kumar, Dr. Vinod George, sir, the HODs, Professor Jayakumar, Professor Shiba, ma'am, Dr. Smita Molmis, Professor Vinod Oyam, and Professor Vinish Kumar for their felicitations, support, and wishes. Thank you all. Now, I would like to thank our course coordinator, Ms. Radhika Nair. She is the backbone behind this FDP. Her hard work and sincere efforts made this FDP recent advances in earthquake engineering possible. Thank you, ma'am. I thank all my colleagues, Professor Shruti, Professor Srividya, Professor Govind, Professor Ajit, Professor Suraj, and Professor Ben Thomas for your supports throughout all the phases of this FDP. Last but not the least, I thank all the participants who have gathered here in this online platform for making the inaugural session complete. Hope all of you will have nice sessions of FDPs and this will help you to move one step forward professionally. I wish all the best for all the participants. Thank you. Thank you all.
Thank you all. First session will start now. All of you join through the link provided. Thank you.
Dear participants, the same link will be used for the FTP first session also. So please continue to remain here. We'll start the technical session in this link.
Madam, are you able to see my PPT?
Yes, sir.
Point.
Yes, sir.
I welcome Professor Sudhi, LBS College of Engineering, Kasaragod, to introduce the speaker to the audience.
Okay, ma'am. Welcome all of you to the first session. Let me introduce our resource person, Professor Dr. Katta Venkataramana. He is a senior professor at the Department of Civil Engineering, National Institute of Technology, Karnataka, Surathkal. He obtained his bachelor's degree in civil engineering from University of Mysore, master's degree from Kagoshima University, Japan, and doctorate from Kyoto University, Japan. He worked as a postdoctoral research fellow at University of Oxford, UK. He is serving NITK Surathkal as a professor since 2002. Professor Venkataramana has served as the head of the Department of Civil Engineering at NITK 2 times during 2009 to 2010 and 2013 to 2014. He was the Dean, Academics, and the Chairman of Board of Studies at NITK for 3 years during 2014 to 2017. Professor Venkataramana's current research interests include structural engineering, in particular structural dynamics, and earthquake engineering. He has supervised a large number of undergraduate and postgraduate students in their thesis research. 19 PhD scholars have completed their PhD degree under his guidance. Professor Venkataramana has delivered many invited talks in India and abroad. He was a visiting professor at Kumamoto University, Japan during 2010 to 2011. He is a fellow of Institution of Engineers India, and he is serving as the chairman of Institution of Engineers India, Mangalore Local Center. On behalf of the coordinators and participants, I welcome you, sir.
Okay. Thank you for the introduction, madam. Shall I start?
Yes, sir. Thank you. Yes, sir. Please.
I will make this full screen. So I would like to speak on this topic, introduction, that is engineering seismology and lessons from past earthquakes.
So just a minute. The full screen is not visible, sir.
Not visible. Huh?
So, can you go to view full screen slideshow? Full screen.
Full screen slide.
Yes, sir. Yes, sir.
Are you able to see full? No?
No,
Side?
sir.
Sir, please press F5, sir. Directly it will go for full screen.
F5. One minute, I will stop and once again join. Let us see.
So would it be possible to present the full screen instead of
Yeah,
Tab.
this I will try now.
Yes,
Are you
sir.
able to see full screen?
Yes, sir.
Okay, okay. So, initial part of my lecture will be about the generation of earthquakes and how earthquakes are measured and so on. That is engineering seismology. And the later part will be devoted to damage pattern observed in some of the past earthquakes, and so that we can have an idea what are the probable reasons of damage. So now vibrations of the Earth's surface caused by waves originating from a source of disturbance in the Earth mass is called earthquake. Earthquake may be caused by volcanic eruption or by strain building process inside the Earth mass. The main thing is earthquakes are unpredictable. Here on the left hand side, we have the schematic map of the diagram of Earth's interior. We have core, inner core, outer core, then mantle, lower mantle, upper mantle, and Earth's crust. And if you look here, the temperatures, inner core around 4,300 degrees centigrade and consists of solid iron mainly. And outer core here around 3,700 degrees centigrade, and near the crust 1,000 degrees centigrade. This mantle is in plastic zone. So inner core solid, then liquid, plastic, and then we have the Earth's crust. Because of this temperature and pressure gradient inside the Earth, there will be circulations in the mantle. So the hot material comes up, cools down, and then again moves, as you can see here. So this is similar to what happens when we heat water in a beaker. So similar thing is happening in the Earth also, and this results in the earthquakes. Earthquakes are more appropriately explained using the plate tectonic theory. Here the circles actually indicate the earthquakes, and this shows the magnitude. Bigger the diameter of the circle, the greater magnitude of the earthquake. So as per this plate tectonic theory, Earth's outermost surface is broken into several rigid plates which float on top of a more fluid zone, much in the way icebergs float on the top of the ocean. And as these rigid plates move in different directions, they will collide with each other or move away from each other. Now we will see how the continents were formed. This figure shows the situation about 225 million years ago, when the continents were joined into one supercontinent that the geologist Wegener called Pangaea. And by 200 million years ago, this continent had divided into two large subcontinents, Laurasia and Gondwana land. You can see Laurasia and Gondwana land. And then in the great southern subcontinent, Gondwana land, South America and Africa were connected with each other and with Antarctica. You can see here in figure C1. So South America and Africa were connected with each other and with Antarctica, India and Australia. This is roughly the time when the first flowering plants began to appear on Earth. By 65 million years ago, about the time when dinosaurs became extinct, the continents had divided into positions closer to the present day configuration. As of now, the continents resemble the configuration shown here. So one supercontinent has divided into several continents, and this shows the movement in the time scale in terms of millions of years ago. So 200, 180, 130, 100, and so on. This is the present day configuration. Now, if you look at the tectonic plates, there are 7 major plates and several minor ones at present, and they move a few centimeters a year, riding on semi-molten layers of rock underneath the crust. These 7 major plates are Pacific plate, North American plate, or South American plate, Eurasian plate, African plate, Australian plate, and here Antarctic plate. So most of the earthquakes have occurred along these plate boundaries. And here you can see the movements of the plates. For example, this is the Eurasian plate. Here plates are moving away from each other. And this is Indian plate colliding with the Eurasian plate. Plates moving towards each other. Or if you look at the North American plate and Pacific plate, here the plate movement is sideways here. Here South American and African plate, here plates are moving away from each other. So as the plates move, they pull apart or collide, unleashing earthquakes along their boundaries. So sea floor spreading, mountain forming, valleys forming, subduction, all these are results of tectonic plate movement. And when the plates collide, you can experience earthquakes. And you can see here, it's a boundary. Boundaries of the plates, most of the earthquakes have occurred. You can see the circles concentrating along the plate boundaries. And the right-hand side, we see the San Andreas Fault Zone, California. This is around 1,000 kilometers long fault system, marking the boundary of North American and Pacific plates. Now, about measuring the earthquakes, we have so-called magnitude and intensity, 2 scales. Magnitude, it estimates the amount of energy released at the source of the earthquake. Commonly used scale, local magnitude scale or Richter magnitude scale. This name Richter is in honor of seismologist Charles Francis Richter of USA. For a given earthquake, there will be one value of magnitude, and it will indicate the amount of energy released. We also have a scale, measuring scale called intensity. It is a measure of the degree of earthquake shaking at a given location based on the amount of damage. Commonly used scale, Mercalli intensity scale or modified Mercalli intensity scale. It is a qualitative measure, and the value of intensity will vary as we move away from the source of the earthquake. Whereas in the case of magnitude, there is only one value because it estimates the amount of energy released at the source. Sorry. The frequency of occurrence of earthquakes is shown here. Great earthquake, major earthquake, strong earthquake, these actually cause considerable damage, structural damage, and loss of property and lives. Great earthquake, magnitude 8 and higher. At least one earthquake somewhere in the world we can expect in a year. So this shows the frequency, annual frequency occurrence in a year. So major earthquake, magnitude 7 to 7.9, around 17. 6 to 6.9 magnitude, around 134 earthquakes. Then moderate and light earthquakes, this is the annual occurrence data. Light earthquakes, no damage, but you feel it. 4 to 4.9, around 13,000 earthquakes. And very minor earthquakes, mainly recorded by instruments. It will show actually the seismicity of the region, and mostly seismologists, geologists are concerned here. So as civil engineers, we are mostly worried about these earthquakes shown in yellow or in red color, where the structures will experience strong shaking, and if not properly designed, we can expect some damage. Greatest recorded global earthquakes are shown in this slide. 1960, earthquake of magnitude 9.5 occurred in Chile, that is in South America. 1964 in Alaska, magnitude 9.2. Then 2004 Indonesia earthquake, magnitude 9.1. Very large number of people died in this Indonesia earthquake. Even south coast, Tamil Nadu, Kerala all experienced tsunami. Sri Lanka also experienced tsunami during this earthquake. Then magnitude 9, 1952. Again in 2011, in Japan, more than 50,000 people died. There was tsunami, and also a nuclear reactor was damaged. Chile earthquake, magnitude 8.8, and so on. China, 7.9 magnitude earthquake in 2008. 2010 in Haiti, Central America, magnitude 7.1. Magnitude was on the lower side, but a lot of people died because of the poor state of construction of dwellings. That is about the magnitude. Intensity, as I mentioned, it is a qualitative measure of the actual shaking at a location during an earthquake, and is assigned Roman capital numerals. Magnitude is an open-ended scale, whereas intensity, it varies from 1 to 12. Intensity varies from 1 to 12. 1 is felt by almost no one. Intensity 2 felt by very few people. If you compare this intensity with the magnitude scale, actually it is not possible to compare, but we can say near the source of the earthquake, this may be the intensity, and this may correspond to these values of the Richter scale. So the damage mainly happens when intensity is 7, intensity 8 and higher. Specially designed structures damaged slightly, others collapse. Intensity 9, all buildings considerably damaged, many shift of foundations, noticeable cracks in ground. Intensity 10, many structures destroyed, ground is badly cracked. Intensity 11, almost all structures fall, bridge wrecked, very wide cracks on ground. Intensity 12, total destruction. So intensity 12, near the source of the earthquake, magnitude will be 8 and higher. So this actually compares the Mercalli intensity scale and Richter magnitude scale. And points joining equal intensities we call isoseismals. This is from the Bhuj earthquake. This is the intensity near the epicenter of the earthquake, intensity 10. And as we move away from the epicenter, the damage will be less. So intensity value also reduces. Intensity 9, 8, 7, and so on. So earthquakes are measured mainly using the magnitude scale or intensity scale. Now, if you look at the Indian plate, as I mentioned, due to tectonic plate movement, Indian plate, which was very far from the present day, for example, this is 71 million years ago, then this is 55 million years ago, and so on, 24 million years ago, the position, 10 million years ago, and this is the present day configuration. So India makes contact with southern margin of Asia about 55 million years ago. And this is the thrust boundary. Actually, Indian continent is pushing under the Eurasian plate. And because of this collision, Himalayas have been formed. The birth of Himalayas is shown here. 60 million years ago, India collides into the Asian plate. This movement is what eventually causes the Himalayan range. As the two plates push against each other and the Earth's crust is squeezed upwards. So earlier there was so-called Tethys Sea. So this is the Indian plate and Asian plate, heavy sediments and light sediments. So it is moving here. So these sediments are pushed upwards, squeezed upwards, as you can see here. This is 40 million years ago. Heavy sediments on the ocean floor sink under the Asian plate, slowly closing up the Tethys Sea. The Indian plate is colliding even deeper into Tibet. So you can see the both sides of the sea are coming here. So this sea is closing up. 20 million years ago, the Tethys Sea is completely gone and heavy sediments from the ocean floor are pushed up from the Himalaya and the Tibets begin to rise. This Indian plate, this Eurasian plate, and sediments are pushed up and Himalayas are being formed. And this is the present day configuration. Through GPS technology, we know that 19 kilometers below the surface of the Earth, India continues to move northward under Tibet at 18 mm per year. The greater Himalaya, including Everest, are rising at approximately 5 mm per year as a result of the squeezing motion between India and Tibet. So Himalaya are rising approximately at 5 mm per year, and seismologists predict that in 10 million years from now, as the boundaries of Nepal approach each other, Nepal ceases to exist. The Himalaya, however, still exists as foothills and mountains continue to form over the advancing edges of India. So because of this collision of Indian continent with the Eurasian continent, Asian continent, a lot of earthquakes are occurring in this region. This shows the seismicity from 1973 to present. Even smaller earthquakes have been shown here. And if you look at the tectonic map of India, this is the thrust boundary. So most of the earthquakes have occurred here. And also we have the fault zones shown in this red color. Some are closer to these tectonic boundaries and some are away also. This we call the earthquakes occurring here, we call intraplate earthquakes. Intraplate earthquakes, whereas occurring along the plate boundaries, we call interplate earthquakes. So many earthquakes have occurred away from the plate boundaries also. Earlier, we saw the largest earthquakes all over the world. Now coming to our country, there are records of earthquake in Bombay in 1618. Then in Delhi, 1720, magnitude 6.5. Bengal earthquake, 1737. Around 3 lakh people lost their lives. And then Kutch region also highly seismic. In 1819, there was an earthquake of magnitude 8. And these towns, Tera, Katara, Matala, razed to the ground. 1833, Bihar earthquake, magnitude 7.7. 1897, Shillong earthquake, magnitude 8.7. There was widespread destruction in Shillong. Then Himachal Pradesh, 1905, 1906, and so on. 1934, Bihar, Nepal, magnitude 8.3. Large number of border area people were killed. 1941, in Andaman, there was an earthquake, magnitude 8.1. And recent earthquakes, 1943 Assam, 1950 Arunachal Pradesh, China border. Then we have these earthquakes around magnitude 6 to 7. In 1967, there was an earthquake in Maharashtra, Koyna region. This is said to be due to building up of pressure in the pores, water pressure in the pores after the building of Koyna Dam. So this earthquake, Koyna earthquake, is said to be due to the effect of building Koyna Dam. Then 1988, Bihar, Nepal earthquake, Uttarakashi earthquake, Uttarakhand. This earthquake, 1991, also caused widespread damage. Then 2004, Indonesia earthquake of the west coast of Sumatra, magnitude 9.1, we discussed earlier also. A lot of damage happened in India due to this earthquake. Then Sikkim, Nepal earthquake, 2011. 2015, Nepal earthquake, border region in Bihar also, we saw widespread damage. This shows the seismic zoning map of India as per IS 1893, that's Earthquake Resistant Design Code. Our country is divided into 4 seismic zones, zone 2 to 5. Seismic disturbance up to magnitude 4.9 in this zone 2, shown in blue color. Yellow color, moderate risk zone, magnitude up to 6.9 we can expect. So Kerala, coastal Karnataka, parts of Tamil Nadu, Hyderabad, Andhra, all come under this region. Then zone 4, shown in green color, high risk zone, magnitude up to 7.9 we can expect. And zone 5, entire northeast and parts of Kashmir, Uttarakhand, UP come under this zone 5, very high risk zone. We can expect earthquakes of magnitude 8 and higher. So if you look at zone 3, 4, 5 together, about 60% of our country, 60% of our country comes in this zone. So we need to design our structures for earthquakes of for moderate to very high earthquakes, magnitude 6.9 and higher. So this shows the importance of considering earthquakes in our designs. If you look at a simple static analysis, if W is the vertical force, gravity force, depending on the seismic zone, the horizontal load induced due to earthquake will vary. If you consider zone 2, the zone factor Z is 0.1, zone 3 0.16, zone 4 0.24, and zone 5 0.36. So if you consider a 100 kilonewton value of W, the value of H will be 10 in zone 2, 16 kilonewton zone 3, zone 4 24, and zone 5 36 kilonewton. This is very simple approximate estimation here. There we have to give the weightage to the soil conditions, importance of the structure, and how the structure is built, materials, etc. Just for thumb rule, I am showing you how, depending on the zone, seismic zone, the value the horizontal force which we need to consider will greatly vary. Now coming back to seismology, the basic terms explained here. Focus, also known as hypocenter. This is the point on the fault where the slip starts. This is the fault rupture starting from this point. This is known as focus or hypocenter, source of the earthquake. And the point vertically above on the ground, we call epicenter. Epicenter. And distance from epicenter to focus or hypocenter, we call focal depth. It is an important parameter in determining the damaging potential of an earthquake. Most of the damaging earthquakes have shallow focus with focal depths less than about 70 kilometers. So if the focal depth, if this depth is less than 70 kilometers, we can expect larger damage. And the distance from epicenter to any point of interest is called epicentral distance. So normally during an earthquake, if you look at the newspaper, they will mention what would be the focal depth and also where the epicenter is located. Now, effect of earthquakes is to generate seismic waves. So if this is the source or hypocenter, focus of the earthquake, earthquakes waves or seismic waves generate from this point, travel within the earth and also along the surface of the earth and reach the point of interest. We travel within the earth, we call body waves or deep waves. And these waves further two types, P waves or primary waves, and then S wave, also known as secondary wave or shear wave. So these primary waves are fastest. Particle motion is shown in the right hand side. It is along the wave propagation direction. So you will have extension and compression, push and pull effect here in primary waves. Whereas S waves, particle motion is side to side or up and down, up and down. It is shown here, side to side and up and down. Then when they reach a surface, they travel along the surface. We have love waves where the particle motion is sideways in horizontal plane, and then Rayleigh waves which are elliptical in the vertical plane. So we have seismic waves classification, body waves or deep waves, and then surface waves. And then these body waves or deep waves further classified as primary wave and shear wave or secondary wave, and surface waves classified as love waves and Rayleigh waves, and classification mainly based on the particle motion. And as these waves travel the interior of the earth, depending on the soil conditions, these waves get magnified. So this fault rupture, body waves, and then travel along the surface. And right hand side, it is shown more clearly. This is rocky ground and this is soft ground. So the seismic waves are magnified. Seismic waves are get magnified when they pass through soft soil. And we can expect more shaking and more damage on structures on such grounds if no care is taken about their foundations. This slide shows how the earthquakes are measured. They are measured using an instrument called seismograph. So left hand side, a schematic diagram is shown. Earthquakes generate seismic waves which can be detected with a sensitive instrument called a seismograph. Fundamentally, a seismograph is a simple pendulum. When the ground shakes, the base and frame of the instrument moves, but the inertia of the bob, inertia keeps the pendulum bob in its place. It will then appear to move relative to the shaking ground. As it moves, it records the pendulum displacements as they change with time, tracing out a record, which we call seismogram. So the instrument is seismograph and the record we call seismogram. So this is a schematic diagram. Right hand side we have the seismographs of today. These are very sophisticated instruments and they operate by measuring the amount of electrical energy which is needed to keep the mass centered in the housing in the presence of strong ground shaking. So these modern day seismographs or seismometers, they can record a wide range of seismic signals, both very small, very minor earthquakes to very large damaging earthquakes also. This shows a shaking record. As I mentioned, seismogram is the record, whereas seismograph is the instrument. This is the typical plot. The P waves travel fastest, primary waves travel fastest and arrive, followed by secondary waves, S waves, and then we have the surface waves. And most of the damaging earthquakes, it's mainly because of this motion when the surface waves reach the structures. This area we call strong motion, especially random, time dependent, cyclic. So these are the characteristics of this strong motion. The entire this record may be several seconds or a few, 1 or 2 minutes. This is the plot of Bhuj earthquake, 2001 Bhuj earthquake. For 2 minutes, time is shown along x-axis in seconds. So 140 seconds, 2 minutes 20 seconds. And strong motion is here from about 30 seconds to 60 seconds. So this is the strong motion. The top figure shows the acceleration. As you know, earthquake-induced motion creates inertia force, which is mass of the structure into acceleration. So normally we are interested in the acceleration. But if we have this data, we can get the displacements also. Velocity displacements also we can obtain. So this is the actual plot from the Bhuj earthquake taken in Ahmedabad. So one building is there, passport building. It was instrumented, so data was obtained from there. Locating the shaking, seismologists locate earthquakes by measuring the time between the primary wave and secondary waves in a seismogram. After a seismogram feels an earthquake, scientists compare the time difference of these waves to figure out how far away the earthquake is. Let us say the instrument is located here. So from the record, if you can identify the time difference between primary waves and secondary waves, if we calculate, let us say earthquake has occurred at 4,800 kilometers away. So we can draw a circle like this. And if this is another instrument, seismograph, and based on the data here, let us say the earthquake has occurred at 2,800 kilometers away. So we can draw a circle. So the meeting points of these two circles, we have these 2 points. And then if you have one more instrument, say here if we record the time and find out the distance to the source of the earthquake, and if we draw a circle like this, the 3 circles are meeting at this point. So this will indicate the epicenter. It takes at least 3 seismograms to locate exactly where the
Mic is mute.
Hello, sir. Mic is muted.
just now or?
Yes, sir. It's okay now.
Okay. Are you able to see now or shall I? Are you able to see full screen?
It's not in the full screen mode, sir.
Now?
No, not full screen, sir. Slideshow. Slideshow.
Can you see entire screen?
Yes, sir.
Okay. So that is about the measurement of earthquakes, seismic waves, how earthquakes are generated and so on. Now let us look about some of the past earthquakes. Based on this earthquake protection by Coburn and Spencer, published in 2002, if you look at the data, 1900 to 1949, about 7,95,000 fatalities. Most of this was due to collapse of masonry building. Then we have, this is due to collapse of timber, wooden buildings, then RC buildings, fire, landslide, and other causes. And if you look at the data from 1950 to 1999, share of 7 lakh fatalities, still collapse of masonry building is major culprit. Not only in India, in China, in Latin America, in Europe, there are a lot of masonry buildings. So this is the seismic resistance of masonry buildings is still very important. Then the number of buildings constructed using RC, reinforced concrete, are much more compared to earlier part. So this is due to collapse of RC building. Then collapse of timber building compared to earlier data, this has reduced because wooden construction has reduced. Then this is due to fire, landslides, and other causes. So if you look at the data, collapse of masonry building and collapse of RC building, they form a major part of causes of fatalities during the earthquakes. Some of the failure patterns, typical failure patterns will be discussed now. This is from the Bhuj earthquake, magnitude 7.7 earthquake, separation of roof from the wall. Here also, separation of roof from the wall. This is 2011 Sikkim earthquake, magnitude 6.9. Failure of junction of 2 orthogonal walls. This is 2 orthogonal walls in unreinforced masonry building. Then these are from the 1993 Latur earthquake. This is from the Bhuj earthquake. Masonry buildings, we can increase the seismic resistance by providing bands. Bands are nothing but wooden beams or RC beams at regular intervals, at plinth level, at lintel level. This helps the building to behave as a single unit. If the building has pitched roof, we have to provide proper connections here, as you can see here. So even 2-story building, we can provide earthquake resistance features. And the buildings which have been provided with these kinds of bands have behaved, have performed well during some of the past earthquake. This is from the Kilari earthquake, a building with horizontal lintel band, no damage. Whereas here, no horizontal lintel band, collapse of the roof and walls. And right hand side here, this is 2001 Bhuj earthquake, a bentonite factory building. Cracks were developed in the walls, but because of these bands at regular intervals, this has helped to withstand the shaking. Here also, good performance due to lintel bands and plinth band. And as you can see, this helps, these bands will help the building to behave as a single unit and to ensure box action in a masonry building. So good connection at wall corners, good connection between walls and foundation, small openings, and lintel band. good connection between roof and walls. These are the essential requirements. We can get a lot of information, as many of you are already aware, from IIT Kanpur, National Information Center for Earthquake Engineering, this website. We can get a lot of information. Then these are also some of the damage patterns. Wall fracture during Bhuj earthquake. You can see here. Out of plane collapse of peripheral walls. This is 1991 Uttarakashi earthquake. Stone masonry wall has collapsed. This is Nepal earthquake 2015. Out of plane failure of walls in Bhaktapur city. The typical types of damage in masonry buildings. So this is direction of seismic action. So this wall is perpendicular to this. So we can expect here out of plane bending. And in the walls which are along the direction of seismic action, you can expect these kinds of diagonal cracks or shear cracks developing in the wall. So some of the damage patterns: cracks between walls and floor, cracks at corners and wall intersections, out of plane collapse of perimeteral walls, then diagonal cracks, partial disintegration, and partial or complete collapse of the masonry building. So those are some of the damage patterns in masonry buildings. Earthquake resistant design seeks to produce structures that can withstand a certain level of shaking without excessive damage. If you look at the difference between gravity loads and earthquake loads, this is the gravity load. If you consider a frame, this is the stretching of members and location of tension at these locations. So if you compare this with earthquake load, here earthquake changes direction. So when left to right motion, when earthquake induced motion results in vibrations left to right. So these are the locations of tension, stretching of members. When it is from right to left, these locations get reversed. These locations get reversed. Bending moments will develop like this. So we need to provide tensions steel on both faces of members. So the reinforcement requirement for earthquake shaking is quite different. Earthquake induced shaking is quite different than when we consider only the gravity loads. Now we will discuss some of the damage of RC buildings. RC walls with unreinforced masonry infills are most common in our country. This can be the map of anywhere in our country where we have extensive RC buildings. And during Bhuj earthquake, 132 such low to medium rise structures collapsed in Ahmedabad itself, several hundred kilometers away from the source of the earthquake. Earthquake source was in Bhuj area, in Bhuj, near Bhuj, in the Kutch region, which is around more than 100 kilometers away. Still, many structures in Ahmedabad got damaged. Some of the damage patterns, one is open ground story. Open ground story buildings with masonry infills only in the upper stories. Severe deformation demands at ground story column. This is the ground story. If you don't consider the masonry infill, if you design as a bare frame, this is the expected deformation pattern. However, because of masonry infills, if we not properly design the ground story columns, there can be large deformation at this level, ground story level, and this floor will be crushed. Similar thing is happening here. Soft story collapse of the right wing of the building. The left wing without soft story is apparently undamaged. So this is the ground story here. Here, ground story, we had opening like this. So this has resulted in the crushing. So this is the, you can see the water tank columns here. So the ground story has settled. Same thing, right hand side, and Gandhidham, Sayaji Hotel failed at the soft ground story. Ground story has been crushed. This is a closer view. These are the ground story columns. Then short column effect. Unreinforced masonry infills placed up to partial height adjoining the columns reduce the column height. So we have this masonry infill. So the column height is reduced. So in such cases, we have the short column effect. They attract large shear forces. This is the damage pattern in Bhuj earthquake. In such cases, it is recommended to provide lateral ties at close intervals, which can withstand the shear forces. Bare frame, predominantly a frame action, whereas frame action with bending. Whereas in the infill frame, we can expect shear action. So these, when we have infill walls like this, there will be alternate compression and tension along these diagonals. And this will result in cracks in the masonry wall, as you can see here, and infill walls. And if the strength exceeds, then the walls may fail, as you can see here. This is from the 2016 Manipur earthquake. Another cause of failure is honeycomb action. So this is the concreting of the columns. Normally we do the concreting up to certain height. Then top portion of the column, which we call topi, the concreting is done along with the beam above. However, due to reinforcement, flow of concrete through bottom beam bars becomes difficult. And if no proper compaction is done, there can be honeycombed concrete in this portion, which we call topi portion. Concreting in beam and topi is done together, and with no proper compaction, there can be honeycombing. And when subjected to lateral loads, earthquake-induced motion, we can expect failure at these locations. Failure of the weak concrete in the topi just below the beam. This is from 2001 Bhuj earthquake. Here also crushing and spalling of concrete close to the beam bottom. So honeycombing also results, one of the causes of failure. Then shear cracking of non-ductile columns of open ground story buildings. You can see the lateral ties are provided at distances more than minimum specified in the code. This is a ball pen, you can see the spacing and distance. Here we don't see any lateral ties also. Our code specifies these lateral ties to be provided, and also it is required that we provide 135-degree hooks. And this distance also 10 times the diameter of bars are greater than 75 mm. And when the cross section is more than 300 mm, we need to provide a cross tie at the center. Code specifies very clearly the requirements. So if we don't adhere, we can expect these kinds of failure. This is a damaged school building in Kukuma village in Bhuj earthquake. The closer view, side view of the damaged school building. At this joint, if you see, this is the reinforcement. It has pulled out at the beam column joints. Code specifies the requirements. Anchorage of beam in an external joint. This has to be taken development length plus 10 times the beam diameter. This is top bar and these are the bottom longitudinal bars. If they are not sufficient, the reinforcement will be pulled out, as you can see here. Then damage to reinforced concrete warehouse in Kandla port, Bhuj region, in the Kutch region. short column effect along the outer periphery columns. We saw the damage, whereas interior columns performed well. Then about the torsional effects, this is taken from earthquake tips, IIT Kanpur earthquake tips, how buildings twist during earthquakes. So these are rope swings. These are buildings, single-story building, three-story building. Rope swings and buildings both swing back and forth when shaken horizontally. The former are hung from the top. These rope swings are hung from the top, while the latter are raised from the ground. Identical vertical members placed uniformly in plane of building cause all points on the floor to move by the same amount. If you do the swinging, if these rope heights are same and also swinging is symmetrical, then they will move from the same amount. Same thing happens in the case of building also. If this is the earthquake ground movement, we have uniform movement of floor when we have identical vertical members. However, when there is heavy mass on one side of the building, in the case of swings, for example, if you are sitting on one side, then more mass on one side causes the floors to twist. So this light side of the building, this heavy side, so there will be twisting. And similarly, when there are columns, for example, building on inclined ground, and if you have columns on one side which are of longer height, in such a case, it's similar to swings with unequal ropes. So even if mass is uniformly distributed, because of this effect, there will be twisting when subjected to earthquake-induced motion. We can expect these twisting and torsional effects. Buildings have unequal vertical members. They cause the building to twist about a vertical axis. So we can expect torsion-induced damage. This is from Ahmedabad, 11-story building, Mansi complex, collapsed due to overload from pool at the top. This one side of the complex had collapsed. What you are seeing is the standing portion. This is a schematic diagram. There was a swimming pool at the top, which was not there in the original design. This resulted in center of mass to be shifted to one side. And this is center of stiffness or center of rotation. And because of this separation between CR and CM, there was torsion, the amplified torsional response. And when it fell, it collided with the adjacent building. That was also damaged. In this way, a torsional response, torsional effects also becomes very important if you have irregular shape of the building. So preferred shapes are regular and symmetrical in plan and in elevation. This is product manufacturing unit of reinforced concrete, damage to infill walls and then damage to piping systems. Here also you can see the pipe flange of naphtha storage tank ruptured. In such cases, we can expect secondary damage because of the this release of gases. Then liquefaction, ground settlement due to liquefaction. And in this case, the ground has settled, they constructed a new step and used the building. Then telephone poles collapse due to liquefaction. In saturated sandy soil, we can expect liquefaction during earthquake-induced vibrations. This is old photo. I am here. I was in the team of Bhuj earthquake damage survey. These are professors from IIT Roorkee, Professor Paul, recently expired. Then some Japanese delegation from Tokyo University and Kyoto University. So as a team, just after the earthquake, we had done damage survey after the huge earthquake. Let us quickly go through another 15 minutes. I will quickly go through the earthquake-induced damage from various parts of the world. This is Chile earthquake, 1960. So far, the largest magnitude, 9.5. Chile is in Southern America. The 1960 Chile earthquake is the largest event in modern history and experienced three distinct hazards due to this earthquake: strong ground shaking, tectonic subsidence, and tsunami inundation. This is South America, so this is Chile. And because of this very high magnitude, it induced tsunami also. This is in hours, like 0, 2, 4, 6, and so on. Tsunami even traveled and reached Philippines, Japan, Australia, and so on. And because of soft soil conditions, there were fissures on the ground. This 1960, so photographs in black and white. You can see the fissures, depth of the fissures. People are standing here. And many structures got damaged due to liquefaction. Roads, ports, urbanization, dwellings, schools, water treatment plants, and riverbanks suffered the effects of liquefaction and lateral spreading. This is 1964 Alaska earthquake. You can see the distortion of railway tracks. And here, steel truss railway bridge. Here, the lateral spreading of the banks destroyed the foundations, caisson foundation supporting the structure, allowing it to drop onto the banks. This is 1964 Alaska earthquake, magnitude 9.2. 1964 Niigata earthquake. Some of the 4-story buildings in the Kawangi Shichijo apartment complex settled and tipped as much as 60 degrees. Loss of bearing strength was caused by liquefaction of a sand layer 10 to 15 feet below the base of the affected buildings. The peak ground acceleration did not exceed 0.1 G. G is acceleration due to gravity, 9.8 meters per second square. So 0.1 means 0.1 G, 0.9 meter per second square. Not much, but because of the liquefaction of the sand layer, building collapsed. Building suffered damage, as you can see. So after the 1964 Niigata earthquake, a lot of studies were started. People understood the importance of geotechnical earthquake engineering, and studies about the liquefaction effects became very widespread. This is San Fernando 1971 earthquake. Here also damage to overpass happened because of the ground shaking and the ground failure effects. This is aerial view of collapsed section of the of a dam here. So Niigata earthquake and San Fernando earthquake resulted in the development of geotechnical earthquake engineering, and people realized the importance of considering soil characteristics in the designs. This is Mexico earthquake. Mexico earthquake struck at an early morning on 19 September in 1985, magnitude 8.1. The city suffered large damage due to large magnitude of the earthquake and also ancient lake bed that Mexico City sits in. So this is the source or epicenter of the earthquake, quite far from Mexico City. However, this city is located in soil, in soft soil conditions, reclaimed land. Normally, if you move away from the epicenter, this is seismograms away from, this is at 0 kilometers, at 13, 27 kilometers and so on. If you move away, the shaking is expected to reduce. Mexico City area was 350 kilometers away from the epicenter, but still it caused widespread damage in the city. If seismic waves were traveling through uniform material, ground shaking would be half as strong at 13 kilometers, 1/4 strong at 27, and 1/8 as strong at 50 kilometers. However, this didn't happen in the case of Mexico earthquake. Mexico City is a sediment-filled basin surrounded by hard volcanic bedrock mountains. You can see this area. As waves progress and move towards the softer bed, basin amplification occurs. That is having low frequency and high amplitude. This has shaken the soft sediments of ground like a jelly in a bowl. So high frequency, low amplitude, low frequency, high amplitude. So building resonance, this is low-rise buildings, high-rise buildings, this is medium-rise buildings, 2 seconds buildings. These kinds of buildings got damaged because of the resonance between the seismic wave and natural period of structures. In Mexico City earthquake, as the ground was oscillating at 2 seconds time period, the building of 8 to 20 stories with similar natural period suffered the damage. So here also, in Mexican earthquake also, the ground conditions played an important role in the damage. So this is some of the photographs of damage. Multi-story buildings. So Mexico City had one of the most stringent building codes based on experience gained from earthquakes 1957 and 1979. Still, this resonance in the lakebed sediments and long duration of the shaking resulted in widespread damage. This is 1988 Armenia earthquake, example of damage to unreinforced masonry buildings. And this is 1992 Turkey earthquake, RC building damage, severely damaged, nearly collapsed residential building. Many failure forms such as column shear, joint shear, lack of bar anchorage, we can see in this photograph. 1995 Kobe earthquake. Kobe earthquake occurred early morning, and fire was because people were preparing breakfast, and fire spread very fast, and a lot of lives and property was lost because of this earthquake, post-earthquake fires. And some photographs. This one elevated expressway near this canal, the piers failed. Aerial view of the Hanshin Expressway with 2 spans fallen off supporting piers. Several of these collapses occurred at the locations right next to a canal. Soil conditions may have contributed to these failures. Here also aerial photograph. This portion has collapsed. Just I think driver applied brakes and lives were saved here. Elevated expressway, Hanshin Expressway, failure. Here, right hand side, mid-story collapse, soft story collapse. Maybe there was open space for say meeting hall or conference hall. That story has been crushed here. Then 1999 Chichi earthquake, Taiwan earthquake, magnitude 7.3. This is Taiwan, around 100 kilometers. Peak ground acceleration about 1 to 1.0 g, and damage to the buildings is shown here. Also damage to the dam. Dam suffered. Usually damages like this will result in secondary disasters, especially in the downstream side. This is commercial buildings with soft story at the bottom, complete collapse close to the fault line. Then damage to the highways and damage to roadways. Then structural damages continued. Compression failure of column exposing reinforcement at the base. In the diagram here, left column is embedded in lintel beam, whereas the right column is independent and it experienced local buckling. Then right hand side, this is shear crack in the walls for X cracks, X-shaped cracks. And here due to twisting, the building has fallen. The upper portion of the building undergone 90-degree rotation and crashed into the ground. It happened due to crushing of columns on one side at the ground story. These are damaged photographs from Taiwan earthquake, 1999 Chichi earthquake. The building codes require not more than 50% of the reinforcement to overlap at a single section, and many columns failed at sections where 100% of the rebar overlap took place. And then this is lack of ties, lack of 135-degree hooks. Right hand side, the hoops spacing was another common code violation. The presence of conduits in the column reduces its effective area. You can see these conduits and increasing the possibility of buckling. And in such cases, we need to provide hoops at closer intervals. 2010 Haiti earthquake, magnitude was 7, but large scale damage, X-cracking of the walls, column shear failure, toppling and out of plane wall failure, etc. We observed here. And if you see a poor aggregate shape and grading, you can see here, poorly located construction joints, then formwork embedded in finished concrete, debris left in joints, segregation, voids, honeycombing. These are the culprits of damage, for the damage in this Haiti earthquake. More than 2 lakh people lost lives here. Then 2011 Tohoku earthquake in Japan, magnitude 9, one of the very severe earthquake experienced by Japan. And total deaths were 19,729. And in addition, around 2,559 people were missing. And it caused damage to nuclear installations here. And there was radiation scare in this area. I will skip some of the photographs. Here, damage to non-structural wall, X type of cracking, damage to structural beam. And in this building, there was uplift foundation building left subsided bottom part of the southeast corner column and uplifting of foundation in the north side. So right side there was uplifting and left side, left southeast corner column there was subsidence. So this resulted in damage to this building. Then during this earthquake there was tsunami also, and some of the damage to structures, concrete wall failure due to internal pressurization. Here building has been uplifted and overturned. And here fish market buildings damaged. In this case, we are seeing the bottom side of this building, 2-story RC building. And then, as I mentioned, the buildings which were designed to withstand earthquakes, they suffer damage because of tsunami. Tsunami height was more than what they had planned. And they inundated the pumps which are used for cooling in these nuclear reactors. And this resulted in damage and also nuclear radiation. And a lot of people were evacuated in the surrounding areas. So this is secondary disaster which happened due to earthquake. The earthquakes caused shutdowns and other electrical grid supply problems. The reactor's electricity supplies failed and their emergency diesel generator automatically started. So when there was a failure of electrical grid systems, these emergency diesel generators automatically started and they provided the critical electrical power. However, when tsunami generated arrived shortly afterwards, it flooded the lower parts of the reactors, causing the failure of emergency generators and loss of power to the circulating pumps. The resultant loss of reactor core cooling led to nuclear meltdowns, hydrogen explosions, and the release of radioactive contamination between 12th and 15th of March. So most of the nuclear installations are located near the coastal region and they need to be designed for tsunamis. And although Japanese had considered tsunami height, but the tsunami which came was much more than what they had planned. This is Nepal earthquake, 2015, epicenter of this earthquake. Large parts of Nepal as well as Bihar area also experienced a lot of ground shaking, and there was damage to highways, road network, collapse of masonry buildings, RC buildings, and so on. So as I mentioned, the damage during this earthquake, mainly because of deficiencies in structures, structural construction, design aspects, and also due to soil foundation effects. Now, as I mentioned earlier, earthquakes induce inertia forces. Inertia is inertia force, mass into acceleration. So earthquake force is a function of mass. So by reducing the mass, making the structure light, we can reduce the effects, earthquake effects. And also we make the structure more ductile. If a structure is ductile, its ability to absorb energy without critical failure increases. It allows a structure to undergo large plastic deformation with little decrease in strength, and have the ability, structures will have the ability to sway and back and forth during an earthquake and withstand earthquake effects without collapse. In the inaugural function speech also I mentioned, the structures are nowadays designed to have more ductility, capable of undergoing large deformation. Severity of ground shaking at a given location during an earthquake can be minor, moderate, and strong. Minor shaking occurs frequently, moderate shaking occasionally, and strong shaking rarely. Earthquake proof is very expensive. So we design such that during minor earthquakes, there is no structural damage and there is no damage to non-structural elements also. In the case of moderate earthquakes, there can be some damage to non-structural elements and it should be possible to repair, and no damage to structural elements, that is load carrying elements like beams, columns, slabs, and so on. And in the case of severe earthquakes, major earthquakes, there can be some damage to load carrying elements also. There can be structural damages, but the structure should not collapse and we should be able to save lives. This is the earthquake resistant design philosophy which is being followed in earthquake resistant design these days. I think one of the speakers will be discussing these quotes also in the subsequent lectures. Earthquake resistant design code of practice IS 1893. Recent revision is in 2016. We have 5 parts. Part 1 deals with the general provisions for all the structures and then some aspects specific to buildings. Then part 2 deals with liquid retaining tanks. Part 3 bridges and retaining walls. Part 4 industrial structures. And part 5 of this IS 1893 discusses dams and embankments. I think that is all. I quickly went through the seismological aspects and also some of the causes of failures of structures during major earthquakes. This is the last slide. This is maybe who have visited NIT Kano. Our college, our campus is somewhere here. We call this area NITK Beach. And it's a lighthouse, nearby lighthouse in Suratkal. So this is all. Thank you very much for your kind attention. I'm sorry I took a little bit more time, and if there are any questions, I'll be happy to answer. Hello? Yes, sir.
Sir, questions are posted in the chat box and question and answer session.
Question and answer is here. Which one?
So there is a question. Shall I read it?
Hello? Frequency of earthquakes. How earthquake frequency is predicted. So for earthquakes, microzonation is becoming popular. Ground response characteristics are being analyzed. Although we have divided the country into 4 seismic zones, it is very general, very mega scale. If we want to know the characteristics at local level, we should understand the characteristics, seismicity of the region. And for big cities nowadays, microzonation is being done. I think there will be lectures on ground response in the subsequent presentations. What I have tried to give is the overall introduction about earthquakes and the causes of damages.
So there is another question in the question and answer session. As you said, earthquakes are unpredictable. Some research is being done to predict using artificial intelligence or machine learning. How effective is that, and what are the precursors for doing machine learning in seismology?
Machine learning, sorry, I am not aware. I am not familiar with the research done in that area. Perhaps other speakers may be able to help in this regard. Maybe Shreyasvi madam, who will be talking on third day. She is working in the organization dealing with earthquake prediction. Organization from Italy. It's an international organization. Maybe that question may be posed to her. I'm sure she'll be able to give the related information.
Good morning, sir.
Hello.
Hello, good morning, sir.
Good morning. Good morning.
Sir, I have a question.
Yeah, yes, please.
In one of your slides, sir, you are talking about this seismic zone factors, wherein 100 kilonewton vertically if applied, we can assume that it is lateral load of 10 kilonewton in zone 2, 16 kilonewton in zone 3, 24 kilonewton in zone 3, and 36 kilonewton in zone 4. Right, sir? Sorry, this is the 2, 3, 4, and 5 zones.
Yeah.
And my question is that in actually earthquake code, they will relate that to maybe acceleration, ground acceleration of 0.16 or ground acceleration of 0.10. Just I want to connect these two, sir, this force and acceleration.
This that slide actually gave a very rough estimate of the horizontal force depending on the seismic zone. For that value, we will be multiplying with other factors like ground conditions, soft soil, hard soil, medium soil, and then the importance of the structures, whether school building, office building, residential building, and also depending on the design, whether we have done ductile design detailing or not. Also, it is whether it is masonry building, RCC building, like that. There are many multiplication factors if you refer to IS code. There is Z by 2 into I by R into SA by G. Maybe you know this formula. What I have mentioned is just to give an idea how the seismic zone in which the structure is being built will tell you how much would be the increase in the earthquake-induced force. So it is a rough estimate. You can see compared to zone 1, zone 2, what would be the force in zone 5 for the same vertical load and ground conditions.
Okay, sir. Thank you.
Yes. Chetan? Yeah.
Hello, good morning, sir.
Good morning.
Good morning. Sir, my question is especially related to the frequency of earthquakes. Which frequency is more dangerous for our structures? Means generally the earthquakes are low frequency, high frequency earthquakes. So I'm want that quantification about the frequency. What frequency means, especially 2, 3, 2.5?
No, it will depend on the ground conditions also.
Yes.
Because seismic waves will get amplified. Depending on the ground conditions, whether it is soft soil and so on. So normally, if the earthquake frequency matches with the structural frequency, we can expect resonance, and there can be damage. So I showed you, the Mexico earthquake, the buildings with 2 to 15 story, that is natural period, the ground period was about 2 seconds, and natural frequencies closer to that got damaged. It may not happen in every case. It depends on the earthquake frequency and the structural frequency.
Okay, so I heard about the Bhuj earthquake investigation.
Yes.
Bhuj earthquake investigation, especially in Ahmedabad city. On one side of the river Sabarmati, I think one river is there in Ahmedabad, and of the some frequency of the earthquake, it was 3 Bhuj earthquake frequency. So it was matching with the majority structural frequency, and that's why the collapse was, our destruction was big on one side of the Sabarmati river in Ahmedabad. So that's why I asked that what will be the frequency of earthquake, which will be more dangerous to the structure. Any quantification or 2, 3 hertz or 3.5 hertz. So that while designing our structure, we can see that they shall not match with the regular frequency.
Yeah.
Thank you, sir. Thank you very much.
Thank you.
So there is another question in the chat box by Professor Ansi Matthew.
H is P Z is zone factor, P is the vertical load, horizontal. Can I use this value horizontal for design of base isolator? No. This is just an approximate expression which I gave to show the importance of zone, seismic zone. For design of base shear, there will be other factors also, like damping present, and also the natural frequency which you are considering. Directly, I don't recommend to use this equation. This is just to give an importance, give an idea about the importance of the zone, which how the country is divided into 4 zones and how the loads will be different depending on the zone in which the structure is going to be built. regarding the structural periods of different building types, you can refer to the IIT Kanpur tips. There is one of the tips which discusses mainly the correlation between the structural period. I don't remember the tip number. There are about 32 tips. One of the tips deals with exactly these natural periods of the structures and how they get damaged during which frequency of the ground. Due to lack of time, I couldn't show those slides. So to get a quick information, I request the participants to go through the IIT Kanpur earthquake tips, that is www.nieee.org. In those tips, you will get the answers to many of the basic queries. Okay. So thank you very much. Thank you very much for your kind attention.
So, good morning, everyone. I'm here to present the vote of thanks. I would like to thank our resource person, Professor Dr. Katta Venkataramana, for enlightening us with his knowledge. He gave deep insights into the topic and was really informative. I'm pretty sure the precious knowledge that Sir gave us will definitely help us in our studies and future. On behalf of the coordinators and participants, I'm thanking you, Sir, for this session.
Thank you. Thank you very much. Can I leave now?
Yes, sir. Yes, sir. Thank you.
Thank you. Thank you very much for giving me this opportunity to participate in the FTP and give a few information, basic information related to earthquakes. Thank you. Thank you, Ananda.
Thank you, sir. Thank you very much.
There is a common inauguration at 11 a.m., which was already started by AICT. All of you, please attend the common inauguration. The link is provided in the chat box. Okay. So our second session will start at 11:30 a.m. and all of you, please join the session using the link provided in the schedule. Okay. Thank you all.